What I'm going to talk about in this kind of last piece of the lecture here is how we study climate. So how do we even know anything about what's happening? Where do we get this data from? What's happening with that? So, and I'm going to focus mostly on the United States, although we'll do a little bit of international talk. So in the US, there's a US Group on Earth Observations. So climate is covered within this, as are basically all of these areas. So as far as the US is concerned, they're looking at everything to do with the Earth altogether. There is no one agency that's in charge of Earth observations. In fact, there are many, many agencies and groups within agencies that have some sort of role in monitoring the Earth. So this is just a membership in this group, and it's hard to see next to each one of them, but there's groups within everything, so it's not just the Department of Defense, it's each one of the groups within that. So quite a number of people to coordinate. So right now, and this isn't exhaustive, but this is a pretty good selection of some of the things that we use right now in the United States to understand climate. There's a whole bunch of volunteer surface sites. So these are little weather stations that are run by volunteers. They collect precipitation. If they have decent machines, they can do snowfall and some other little bit more complicated things. That's one spot. Then there are 1,000 sites that NOAA and the DoD and the FAA run together. Those are mostly the ones at airports. So when you hear the temperature or the precipitation, all that stuff given at the airport, that's usually run by these guys. There are 700 global weather balloon sites. They call them radiosondes. And each of those sites, they usually launch a weather balloon once or twice a day. And that gets atmospheric information. To get ocean data, one of the things we rely on is ships of opportunity, which means essentially volunteer ships. You know, you're going to be shipping materials across the ocean, or you're going to sail for fun, whatever it is. NOAA would love to send a monitor with you on your ship, if you don't mind the extra weight. So part of the data we get just comes from whoever will agree to take it. Then ocean buoys. So there's one of the bigger networks is called the Argos network. There's hundreds, maybe more, of buoys in the ocean, which is a great source of data. Gets a lot of information. One of the things with that is there's not a whole lot in the Arctic or Antarctic regions, and also hundreds of buoys is a lot of ocean buoys. But when you think of how big the ocean is, not quite as many.
Are they stationary buoys, or are they following currents?
I think the Argos ones are stationary, although I'd have to check on that. But they do have ones that move with the currents as well, but I don't know the numbers. So for deep ocean temperature and salinity, those measurements are a little bit more difficult to get in detail, so they send out scientific cruises that collect that information, and that's basically the only way to get that. NOAA runs steam flow gauges and tide gauges that basically monitor the water. They have tens of thousands of those, I think, around the United States, so all over the place. That's actually, they're really trying to fix them up right now. They're trying to look for funding to improve the stream gauge system. For soil moisture, there isn't a national monitoring system, but state networks. States try to look at soil moisture, which makes sense because they're the ones worried about droughts, worried about things like that. There are stations on the coast, coastal radars, and special purpose ships in the Arctic, usually military ships that look at ice issues. So all of that, and then at the bottom I have satellites. Most of the rest of the lecture will be about satellites, so I didn't expand on that here. So this is really my particular area of expertise, is how we use satellites for climate monitoring. And something you might not hear about very often, and you probably may never see another lecture on again, so I'll tell you a lot about them. So first I just want to talk a little bit about the connection of space and climate, because I think to some people it seems like a little bit of an odd intersection to be studying or be working in. But actually it's, since almost the beginning of space activity, it's been one of the first areas where we really started looking at climate, looking at the Earth as a whole. So this is a picture called the Blue Marble. It was taken by one of the Apollo 17 astronauts when they were doing the trip to the moon. And it was one of the first times that we created an image of the entire Earth just this thing sitting alone in a huge area of black. And I think, you've probably seen this. I think all the iPhones use this or used to use this for their cover. And it basically just helped change people's mentality about the need to take care of the Earth, about what a fragile place we have. Planetary science is also another place where some of the very earliest climate research actually got started. So in the 70s, NASA was looking at Mars and at Venus, and before they had a lot of information about them, just based on how far they are from the sun and how similar in size and now that they are to the Earth, they thought they could support life. There's still questions about Mars, whether that be possible. But when they got up close and they were able to take measurements and really look at the atmospheres, they found that both Venus and Mars had developed very differently from Earth. So for example, Venus has 300 times more carbon dioxide in their atmosphere, which makes it extremely hot. And they have no significant water vapor. So we have sent stuff around Venus, but we're not really able to land on Venus yet because it's so extremely hot. Mars has an atmospheric pressure about 1% of the Earth, and it has temperatures that are far below freezing. And there's also no apparent surface water. So we know there's ice below the surface, that's been discovered, but we haven't found any liquid water yet on Mars. But just based on kind of images we're able to take and some data we are able to collect, it looks like there was at one time liquid water on Mars. So one of the things that scientists started doing this research in the 70s and saw that this development was so different than Earth and started to ask, why was it so different? I mean, how can they be so similar in location to us, similar in the basic makeup to us, and completely be unsuitable for life? So then they started looking at the Earth. One of the reasons that satellites are particularly good for monitoring changes on the Earth is that they can have global coverage. So most of the climate monitoring satellites or Earth monitoring satellites are polar orbiting. So you can imagine if the Earth is here, they're going essentially over the poles, and you can kind of imagine almost like the Earth is spinning underneath them. So they really can cover basically everything, including the poles, which are areas that are very difficult for us to get ground-based measurements on. So to just give you a sense of that, I talked about these Argos floats. Oh, there you go, 3,000 of them. And there's the coverage in the ocean. So like I said, it looks pretty good on this graph. They're clearly not to scale, so there's a lot less coverage than it looks like. And also you can see the Antarctic and the Arctic, there's almost no information being collected there. With satellites, we can get that information much more completely, much more easily, and they also pass over on a regular basis. So most of these polar orbiting satellites cover the whole Earth about twice a day. So we can see changes, we can monitor very closely what's happening. Satellites are able to measure a lot of the things that we're interested in for climate, and for some of the things, they're basically the only way to do it. So for the solar irradiance, which, that's the energy coming into the Earth from the external system, extremely important for climate. Satellites are really the only way to directly measure that. So that's an example where we really need them. But also for temperature, for monitoring CO2 levels in the atmosphere, methane, kind of basically all of these forcings that we're really interested in, water vapor feedback, clouds, aerosols, all those things are very well monitored by satellites. Because they can get that global coverage and see the changes really pretty rapidly. And the government is aware that this is a good use of satellites. And so actually a lot of the money that the government spends on climate research does go to NASA and some to NOAA. So in 2004, and budgets have gotten a little tighter since then, but in 2004, the biggest amount of climate science research funding went to NASA. So 1.3 billion out of a total 1.9 billion federal government. And NASA, I put a little picture on it, but NASA has actually a wonderful page on climate science. So if you're looking to learn more or get some good images or some good videos or any of that, it's climate.nasa.gov. This image just shows you some of the Earth-observing satellites that NASA has right now. So this is what's in space. Some of these are, actually a number of them are international projects that are a cooperation between us and either Europe, some of them are with Japan, some of them are with a particular country in Europe, such as France or Germany. But we have a fair amount of stuff up there, all looking at different qualities. So just to tell you about a couple of historic satellites that were particularly important. Landsat is run by the U.S. Geological Society, so USGS and NASA. A lot of people don't think of anybody except for NASA and maybe NOAA as running satellites, but there is this one out there. It does passive imaging, which means it basically just looks at the Earth and takes pictures. Mostly does the visible spectrum. I think it has a little bit of infrared. But the big thing that's useful about Landsat is it has 39 years of continuous coverage of the Earth, which I think is pretty amazing for looking at how developments have grown, about how land use has changed, how agriculture has changed, all sorts of things you can see over this extremely long time period. So it's about moderate spatial resolution, which means you wouldn't be able to see your house in these pictures, but you would be able to see highways, for example. All of that data is freely available online, which is not the case for everything, all the satellite data, or for all the data in general. But anyone, Chinese government could go and get all the Landsat data from the past 40 years for the entire world and have that. So it's I think, a huge success story as far as actually collecting the data continuously and sharing it. And they're working now on a satellite called the Landsat Data Continuity Mission. Basically, every single time that a Landsat satellite has gotten close to the end of its life, they've discussed not continuing it, and then at the last second usually decided to do it. You can see here we're really cutting it close, since Landsat 7 is kind of past its lifetime, it's supposed to be over, and then right in the nick of time we're supposed to launch this next one. So we read an article earlier in the class about how difficult it can be to get measurements. So this is one of the things I deal with a lot, that climate is a pretty big issue. There's a lot of political debate about it, but there's not a lot of debate about how much funding we need to give to satellites or to tidal gauges or to, the basis for this whole discussion and our understanding of what's happening. So another satellite, the Nimbus 7, the TOMS, which is a total ozone mapping spectrometer. This is the instrument that really got the first picture of the ozone hole. So when there was all the debate going on about chlorofluorocarbons and what's happening, they were learning more and more about the science. They were in the midst of creating the Montreal Protocol. This satellite was able to create an image that people could actually see, hey, here's the ozone hole, here's the problem. So it had a huge impact on moving that issue forward. This is CSAT. I put this in here just because this was the first active sensing satellite. So whereas the other, like Landsat, for example, just looks at the Earth and takes pictures, CSAT and a lot of satellites now are active sensing. So they'll actually send a signal and look and see what gets back. So you mostly use radar, sometimes LiDAR, which is similar. So this one was looking at ocean information, so polar sea ice and global surface wave fields. So most of the satellites are going to be this passive sensing, where they just look, or the active sensing, where they're sending signals, getting back. There are some really interesting satellites that are a little more exotic, and I wanted to give you this example. This is the GRACE satellite, which is in space right now, I believe. And what it's doing is taking gravity measurements. So the Earth's gravity actually is a little bit different depending where exactly on the Earth you are. And that's what these measurements, and that's what these satellites measure. And the way they do it is they send up these two twin satellites. They send signals back and forth between them. That's a little red lightning bolt. And what happens is, as they go over a part of the Earth that has a slightly stronger gravitational pull, that actually speeds up the satellite just a little bit. And when it does that, the distance between the two gets a little bit bigger. And it can measure, I think, smaller than a millimeter. So these are tiny, tiny changes in how far apart they get. But it gets farther apart, it takes longer for the signal to go, and so then it knows that there's a stronger gravitational pull there. Then this one catches up. They're equal again. If they go over an area with a less strong gravitational pull, that'll slow down the first satellite, make them closer together, it takes less time to send the signal. And it goes on like that. And basically they're creating the most detailed gravitational map of the Earth that we've ever had. And that's particularly useful for things like ice. So we can look pretty easily at the extent of ice, but to know actually the depth and the whole mass of ice, well, sea ice and land ice, is really important, but much more difficult to measure. So that's one of the things this satellite can do. It flies over multiple times. It can tell what the difference in the mass is over time. Okay, there have been some challenges recently for satellite data collection. This is the OCO satellite. It's the Orbiting Carbon Observatory. The idea was to take basically the most detailed carbon measurements from space that we've ever been able to do. So we'd have the first real global coverage of carbon monitoring. Unfortunately, there's a launch failure. In 2009, it went into the ocean near Antarctica, so it is not collecting information about carbon. They decided to do OCO2. They started that in 2010, so really pretty soon after the failure. But it looks like that's going to be canceled in the 2012 budget. So we may not have it. Another launch failure happened 2 years later, another really important climate monitoring satellite. This is the GLORY satellite, which would monitor total irradiance, so that's at the solar radiance, and also look at aerosols. So really get the most detailed information we've ever been able to have on aerosols. Once again, launch failure. For both of these, what happened was you have the rocket and then you have the fairing on the top of the rocket. That has to come off and let the satellite out. Both times the fairing didn't come apart. So it just, again, crashed into the ocean. I put on here, these are the tweets from NASA when it's happening. Can you guys read them? I think they're really sad. So it has, liftoff, Glory is bound for space atop a roaring Taurus XL rocket. Stage O burnout and separation has occurred. 2 minutes into the mission, all systems are nominal. Stage 1 burnout and separation, stage 2 is now burning. We have had a contingency, no indication of fairing separation. The Taurus continues to fly. We have not received confirmation that the fairing did not separate, or we have received confirmation the fairing did not separate. The Taurus does not have sufficient velocity to achieve orbit. Yeah. But NASA has a Twitter feed. There have also been successes. So this is the NPP satellite. It's the NPOS Preparatory Project. And NPOS stands for National Polar Earth Observing System. Yeah. So essentially, these are supposed to be the next generation of our weather satellites. But back when they were designing them, the government decided climate is now something we need to be measuring operationally, the same way we do weather. And so they put a bunch of climate sensors onto these satellites. Then the satellites got really far over budget, really far past their schedule, and a lot of those climate sensors got taken back off. This NPP satellite was supposed to be a test satellite, so it was supposed to go up and test all these brand new instruments that we never used before for weather and climate. And figure out if they work, and then we're going to launch the real ones. But since the real ones are so delayed, this is now an operational satellite. So, so far it's been launched, things seem to be working, so that's good. It still does do ozone measurements, which are important for climate, the solar irradiance, and it looks at cloud properties. So there still are some important climate measurements. Yeah?
What's the difference between climate measurements and weather measurements when it comes to these satellites?
Yeah, so for weather measurements, they look a lot at more specific precipitation issues. So usually with the polar orbiting weather satellites, they're the ones that are used to tell you what's going to happen in 3 to 5 days. So is it going to rain? Is it going to snow? That kind of stuff. That's what they're really looking for. Whereas with the climate stuff, they'll do things like solar radiance, which you don't need for weather, cloud properties in general. So they're not just trying to figure out is it going to rain. They're trying to understand how the clouds actually affect heat transfer in general, things like that. So yeah, and I didn't mention this earlier, but weather and climate are, obviously have a lot of connections, but they're really very different things. So the way I think of it is, weather tells me whether I need to bring an umbrella outside with me. Climate tells me whether I need to own a winter coat. So this is a quick way to think of it. So more bad news on the satellite front. These are 2 other climate satellites that just recently got canceled. I think also either in the FY 2011 or FY 2012 budget. DESNL was supposed to look at water resources. It would help us understand whether CO2 sequestration would work and would be safe. It looks at terrestrial biomass as a carbon sink, and looks at ice dynamics. I also put in there, it was supposed to be used also to help predict earthquakes, volcanic eruptions, and landslides, which isn't necessarily about climate, but seems like a good reason to launch it. The Clario Observatory was really focused on the solar radiation issue. So there's been a number of satellites that measure that, and I've mentioned a couple of satellites already in the presentation that do. But what this one would do is go up and it takes really specific measurements, and it's designed to be used to calibrate all of the other satellites. So that way, instead of having this kind of broken measurement of solar radiance, we keep launching a satellite for a couple of years and losing it, kind of launching another one, we did something that we could calibrate to. But they're not being launched as of right now. There are climate satellites that we are going to launch. These are two that are coming in the relatively near future, in the next maybe 5 years or so. SMAP is a solar salinity mapping, soil salinity mapping. And that's basically something we have never done from space before, so that's the kind of information that helps us know what's happening as far as drought, precipitation, those kinds of things. And then ISAT-2, which is probably pretty obvious from its name, but it looks at particularly Arctic and Antarctic ice and changes in the ice cover. So we talked a lot about what the U.S. is doing, the U.S. programs. There is a fair amount of international cooperation on climate monitoring, or at least efforts at international cooperation. So there's a global climate observing system. There's the Group on Earth Observations internationally, that the U.S. Group on Earth Observations is actually a member of that. And a number of these groups are underneath the World Meteorological Organization. So we do a very good job of sharing weather data internationally. There's a place where all the data goes to. They know what kind of format it needs to be, and they basically share it with everybody in the world. So we get everybody's weather data, they get ours. And there are a lot of people who want to do the same thing with climate, and they've made some steps toward doing that, but it really has not been achieved yet. This slide is very hard to read, but what it's showing here is they came up, the UNFCCC came up with a list of essential climate variables. So these are things that we need to measure. And then one of these international groups came up with a list that are specifically can be measured or could be measured from satellites. So that's these. And all that I want to show on this slide is that some things, so like land cover, you can see kind of in the middle here, there's a huge number of measurements, satellite measurements of land cover, up to over 100, over 200 later in the next few years. Whereas things like surface air temperature, there's none, maybe one in the future. So this is a place where international cooperation could really have a big impact. It's not practical for one country to say, okay, we're going to measure every single one of these things. We'll just, launch a satellite for each one. That's just not practical, not going to happen. But this is a place where you can see that international cooperation hasn't quite been achieved. There are still gaps and there are still huge overlaps.
So then an example, and I assume most of the satellites you were talking about before that got canceled were NASA satellites, or?
Yes.
So when NASA goes through their budget cuts, do you think that this kind of information is driving which ones, like the two you said, are still funded versus the ones that are not funded at targeting kind of new measurements, or does that not seem to be happening?
So they take into account to some extent, and usually what they'll do is they'll take into account ones that already exist. So, for example, with the weather satellites, when they were really off schedule, instead of putting a whole bunch of money and trying to really speed them up, they made a deal with Europe to use one of their weather satellites. But I think they're pretty careful or wary about relying on international satellites that haven't yet been launched, because there's no real good way to be sure that they will be launched. So, until they get a good way to make those agreements, it seems like they're not there yet.
I have a question.
Yeah.
Back on that previous slide. Does it make sense to have a satellite doing surface air temperatures when we have so many ground sensors that do it? Is that one of the reasons it's never been used, is because it's just taking up space of another sensor we can have on it?
Yeah, so Right, so the question is, how big is the benefit versus the cost? So the benefit of doing it by satellite would be, you would get global coverage, so it wouldn't just be, these 11,000 volunteer stations, it would be everywhere. And with 11,000 volunteer stations or 1,000 FAA stations, whether the person does exactly right every single time they take the measurement is questionable, right? Or different places might use slightly different methods. Whereas when you use a satellite, it's all done exactly the same way. So there's really no question of, did they just mess that up, or is their machine broken, or any of that. You just have it completely. But
Does it also promote having multiple sensors then? Having multiple satellites doing the same thing gives us a better, more complete picture.
oh yeah, absolutely.
So we could say that one satellite that you're going to have doing surface air, what if that's faulty? What if its system takes in some assumptions that we don't agree with?
Absolutely. So two things would be, you would never want this chart to be all ones, where that would not be considered success. But also, I don't think, I'm certainly not advocating, I don't think people are advocating for a satellite-only Earth monitoring system. I think, there are some things we can only monitor on the ground, particularly things like deep ocean stuff, for example. But also, it's important to maintain those. And the fact that we've been collecting that temperature record on the ground much longer than we've had satellites is something we probably really need to continue to collect in the same way. So satellites might be able to add to our certainty or add to our information about it, but it doesn't necessarily mean getting rid of what's on the ground. And that's one of the problems actually with this stuff and with climate data collection in general is because you need it over such long time periods and you do want some duplication, the number of, and we want to understand more processes and more details about clouds or aerosols, whatever, it's just an ever-expanding number of things. And so that's one of the reasons that, for me, I'm really focusing on international cooperation because it's just not, with the path we're taking for learning about climate change and monitoring how what we do will affect climate change, you just can't do it as one group, it's just expanding.